By 1969, a machine existed that made even seasoned strip mine supervisors stop talking. The Bucyrus Erie 4250W Big Muskie, introduced for Central Ohio coal, was not simply an excavator. It was a moving industrial ecosystem. Bucyrus Erie literature from the period described it with disarming restraint, capable of removing 325 cubic yards per pass. That single line, printed in a dealer brochure archived in Milwaukee, hides the reality. It was a 27,000-ton walking drag line, powered by 13,800 volts, operated by a small crew inside a steel house the size of a suburban home. Its bucket alone weighed more than a Caterpillar D9. Its boom stretched 310 feet across Ohio clay. It could move 240,000 cubic yards of overburden per day, and it never left the ground. Big Muskie represented peak American faith in scale. Bigger machines, bigger energy, bigger certainty. Yet today its name survives mostly in museum plaques and faded trade magazines. How does a machine that defines an era also mark its end? Long before Big Muskie, Midwestern strip mining relied on rail-mounted shovels and cable drag lines, machines constrained by tracks, crews, and relocation time. Contractors in Ohio and Pennsylvania faced an old-world problem. Overburden thickness was increasing faster than shovel reach. Trade publications like Coal Age in the late 1920s warned that productivity gains were flattening, not rising. The economics were brutal. Coal margins stayed thin while operating costs climbed. Every foot of additional overburden meant another pass, another crew shift, another maintenance window. Rail-mounted shovels required hours to relocate between cuts, and cable systems tangled in wet weather. Contractors calculated that nearly 40% of shift time was spent on repositioning equipment rather than moving earth. Bucyrus Foundry and Manufacturing Company, founded in Wisconsin and later anchored in South Milwaukee, earned early credibility building steam shovels that were heavy, conservative, and dependable. Engineers following William Smith Otis's principles emphasized durability over innovation. They designed around field reality, mud, cold, parts scarcity, operator fatigue. A Bucyrus shovel might dig slower than a Marion, but it broke slower too. Operators trusted them because downtime meant lost contracts, and lost contracts meant bankruptcy. In dealer surveys from the 1920s, contractors used words like honest and predictable. Nobody called them exciting. That restraint became the company's foundation. The economic truth was simple. Coal margins were thin, downtime was fatal, and nobody wanted experimental machines buried in mud. Productivity was capped not by labor, but by reach. By the 1930s, Bucyrus merged with Erie Steam Shovel, consolidating patents, service depots, and dealer confidence. The merger was less about infrastructure than innovation. Erie brought East Coast dealer networks. Bucyrus brought Midwest manufacturing discipline. Together they controlled spare parts pipelines that competitors could not match. Dealer manuals from the era emphasized parts interchangeability and field service trucks, not bold performance claims. One 1934 service bulletin devoted 3 pages to crankcase winterization and half a page to digging capacity. This restraint mattered more than anyone outside the industry understood. During the post-war boom, Bucyrus Erie refined electric draglines like the 120B, offering deeper cuts without radical redesign. The 120B was not revolutionary. It was a cable dragline with a larger bucket and reinforced boom geometry, powered by increasingly reliable electric motors that utilities were learning to supply at remote sites. Operators wrote in dealer surveys that the machines were slow but honest. Cycle times lagged behind newer hydraulic competitors, but electric draglines required fewer hydraulic seals, fewer fluid changes, and fewer temperature-sensitive components. In northern climates, that mattered. Contractors calculated total cost per cubic yard, not peak performance, and Bucyrus Erie's numbers held. Competitors like Marion and P&H existed, but no one was yet gambling on absurd scale. Utilities wanted coal to feed growing electrical grids. Mines wanted predictability to meet contracts. The industry trusted Bucyrus Erie because it behaved like an engineer, not a gambler. Trust came first, and ambition waited. By the late 1950s, Ohio coal seams forced a reckoning. The Muskingum watershed and surrounding regions held vast reserves, but overburden ratios climbed past 15 to 1 in some sites. Truck shovel systems multiplied costs. Contractors faced a mathematical trap. Deeper seams required more overburden removal, but conventional draglines could not reach deep enough without constant repositioning. Each relocation meant days of downtime, crane crews, and revenue loss. Period literature from Engineering and Mining Journal notes contractors quietly asking a forbidden question: what if one machine could do the work of many? At Central Ohio Coal Company, mine planners explored a radical idea: a walking dragline so large it never needed relocation within a single cut. The concept was not new. Walking draglines had existed since the 1910s, but the scale being discussed was unprecedented. Engineers calculated that a machine with a 300-foot boom and a bucket approaching 350 cubic yards could strip an entire seam in sequential passes, walking forward incrementally on massive shoes, never leaving the pit. The economics were seductive: one machine, one crew, one maintenance schedule. But the risk was absolute. If it failed, the entire operation stopped. Bucyrus Erie engineers in South Milwaukee studied house rotation stress, boom compression limits, and electrical load requirements that exceeded what most utility substations could deliver. No brochure promised success yet. Internal feasibility reports from 1960 listed more failure modes than solutions. This wasn't innovation for prestige. It was desperation engineered into steel. The ground was getting deeper and patience thinner. Internal Bucyrus Erie documents from 1962 describe feasibility studies for what would become the 4250W. Engineers confronted realities no dragline had faced: structural fatigue across hundreds of feet of boom, electrical supply at utility scale, and operator control lag inside a moving steel city. Every dimension pushed material science. The boom alone would span longer than a football field, suspending a bucket that weighed as much as a loaded freight car. Structural engineers calculated stress loads using slide rules and early IBM mainframes, modeling flex patterns under dynamic loading that had never been tested at this scale. The walking mechanism alone required reinforced shoes, distributing tens of thousands of tons across Ohio clay without sinking or fracturing. Period patent filings detail stress relief geometry in the boom chords, not elegance, but survival. Each walking step would shift the entire mass forward in a coordinated hydraulic sequence, lifting one side while the other bore full weight. The margin for error was microscopic. A misaligned shoe could crack the frame. A boom flex miscalculation could snap support cables. Electrical engineers designed a system requiring 13,800 volts delivered continuously, more power than some small towns consumed. Substations had to be built on site. Operators would control the machine from inside an enclosed cab large enough to hold desks, control panels, and multiple crew members working simultaneous functions. Coordination delays between operator intention and machine response introduced failure risks nobody had modeled. Every decision had an economic echo. Bigger meant fewer machines, fewer crews, fewer spare parts, but total dependence on one asset. One machine could save millions or stop everything. Assembly occurred on site near Cumberland, Ohio, because rail transport was impossible. No rail car could carry sections weighing thousands of tons. No bridge could support transit loads. The machine had to be built where it would work. Trade photos from 1967 show cranes dwarfed by house sections being lifted into position. Foundations were poured directly into bedrock. Workers described the scale as disorienting, with components so large that perspective failed. One welder recalled in a later interview that he spent 3 weeks on a single boom section and never saw the full assembly. When Big Muskie energized in 1969, operators described the sound not as noise, but as pressure, a constant electrical hum beneath steel, vibrating through the operator house floor. The first test pass moved earth in a single scoop that would have required a dozen conventional machines. Specs shocked even veterans. Bucket capacity of 325 cubic yards, boom length of 310 feet, power draw of 13,800 volts, operating weight approaching 27,000 tons. The walking shoes alone measured nearly 130 feet long. A Bucyrus-Erie brochure understated it. Maximum efficiency in deep overburden applications. The machine worked spectacularly. It moved overburden in passes that redefined mine planning. Cycle times were slower than smaller drag lines, but each cycle moved exponentially more material. Engineers had calculated correctly. The boom held. The walking mechanism distributed weight without ground failure. Electrical systems ran stable under continuous load. Operators learned to anticipate the control lag, adjusting for the seconds between lever movement and bucket response. The machine was perfect. It did not fail. That mattered more than all. Big Muskie's cycle time rewrote mine planning at Central Ohio Coal. Overburden moved in singular passes that eliminated haul truck bottlenecks. Fewer men were exposed to equipment failure. Operators noted smoother digging due to shear mass damping vibration because smaller drag lines shook and jerked under load. But Big Muskie's weight absorbed shock. One operator wrote in a company newsletter that the machine felt like steering a building. The comparison wasn't poetic, it was accurate. Production numbers validated the investment. Big Muskie could move over 240,000 cubic yards per day under optimal conditions, stripping overburden faster than any combination of conventional equipment. Central Ohio Coal recalculated cost per ton projections and realized they had underestimated efficiency gains. But maintenance crews noticed something else. Every component was bespoke. No dealer yard stocked replacement parts. No service truck carried backup systems. When a motor failed or a cable frayed, replacement meant custom fabrication and shipping delays measured in weeks. Downtime on Big Muskie didn't just stop one machine, it stopped the entire operation. Bucyrus-Erie engineers had designed redundancy into critical systems, but redundancy could not eliminate dependence. The electrical system required utility-grade components. The boom used custom forged steel. The walking shoes wore slowly, but replacements had to be cast individually in Wisconsin and transported by specialized freight. Contractors visiting the site saw the capability, but also the fragility. One machine doing the work of many meant one failure point. Efficiency came with fragility, yet the machine kept working. Through winters and summer heat, through operator turnover and parts delays, Big Muskie moved earth. It became a reference point, the impossible made operational. Nothing else could replace it, including itself. Utilities toured the site in the early 1970s, bringing engineers and financial analysts to witness what Coal Age called the future of surface mining. Trade magazines speculated about a fleet of mega draglines transforming Appalachian and western coal fields. Bucyrus-Erie received inquiries from contractors in Wyoming, Montana, and Pennsylvania. The company explored feasibility studies for even larger machines. Engineers sketched draglines with 400-foot booms and buckets approaching 400 cubic yards. The logic seemed sound. If one Big Muskie worked, why not two? Why not 10? But no second Big Muskie followed. Financing balked. Insurance premiums soared. Lenders saw a single asset risk that terrified actuarial models. If Big Muskie failed catastrophically, Central Ohio Coal faced bankruptcy. Replicating that risk across multiple sites meant multiplying exposure, not spreading it. Contractors wanted the capability but could not stomach the dependence. Dealers, who profited from parts, sales, and service contracts, realized mega draglines eliminated their core revenue streams. A fleet of smaller machines meant continuous parts turnover. One giant meant occasional custom orders. Bucyrus-Erie faced a paradox. They had proven that scale worked, but scale could not scale. The engineering was sound. The economics were impossible. Competitors watched carefully. They did not see a revolution to join. They saw a ceiling to avoid. Innovation hit its limit not in steel, but in spreadsheets. Being first did not mean being copied. Inside Bucyrus-Erie's South Milwaukee offices, pride mixed with unease through the mid-1970s. Big Muskie proved that extreme scale was achievable. Engineers had conquered materials, electrical, and operational challenges that textbooks said were unsolvable at that magnitude. Trade publications featured the machine in cover stories. Universities brought engineering students to study it. Competitors acknowledged its technical brilliance. But the company also proved that extreme scale could not be commoditized. Big Muskie remained singular, a custom achievement, not a product line. Meanwhile, Caterpillar and others refined smaller, modular systems with stronger dealer reach and standardized components. Hydraulic excavators improved cycle times. Electric mining shovels adopted refined bucket designs that Bucyrus Erie had pioneered, but at conventional scales, contractors could finance and maintain. The industry absorbed the lessons: deeper digging, electric drive efficiency, walking mechanisms for stability, but they applied those lessons to machines that dealers could stock and operators could replace. Bucyrus Erie's competitive advantage eroded not through failure, but through diffusion. Every innovation Big Muskie demonstrated became available in smaller, safer, cheaper packages. The company still built excellent draglines. Operators still trusted the name, but the market was shifting toward flexibility, not dominance. The future shifted sideways. The industry learned, just not the lesson Bucyrus Erie needed. Competitors did not build monsters, they built networks. Marion found its dealer service model, guaranteeing parts delivery within 48 hours to major mining regions. P&H focused on modular electric shovels that contractors could finance through regional banks rather than specialized industrial lenders. Caterpillar expanded its mining division with hydraulic excavators that shared components with their construction lines. Mechanics trained on bulldozers could service mining equipment without specialized schooling. The strategy was invisible to engineers, but devastating to market share. Bucyrus Erie's draglines remained superior in raw capability, but capability alone did not win contracts. Contractors calculated total ownership costs, purchase price, financing terms, parts availability, operator training, resale value, and downtime risk. Smaller machines scored better on every metric except peak performance. A fleet of 3 120-yard draglines cost more than a single 325-yard machine, but they offered redundancy, flexible deployment, and dealer support that Bucyrus Erie could not match. Trade shows in the late 1970s revealed the shift. Caterpillar booths featured financing calculators and parts availability maps. Marion emphasized service response times. Bucyrus Erie displayed technical specifications. Engineers admired the draglines. Contractors signed contracts elsewhere. The market had learned what mattered. Scale invited competition, but not imitation. Coal demand softened in the early 1980s as nuclear power expanded and natural gas became more accessible. Utilities renegotiated contracts. Mines postponed expansion. Interest rates, driven by Federal Reserve policy targeting inflation, rose above 15%. Contractors could not finance new equipment at those rates. Existing fleets ran longer between replacements. The used equipment market collapsed as sellers outnumbered buyers. Big Muskie kept working. The machine remained mechanically sound, operationally efficient, and economically productive within its specific application. But that specificity became the problem. Central Ohio Coal could not redeploy the machine to different sites. They could not sell it to recoup capital. They could not mothball it without losing their stripping capacity entirely. Single asset risk, theoretical in 1969, became physical reality. Lenders who had financed the operation tightened terms, seeing exposure they could not diversify. Across the industry, contractors with modular fleets adjusted. They idled some machines, sold others, and shifted crews between sites. Flexibility absorbed market shocks. Bucyrus Erie's customers had no such options. Those who had invested in mega draglines faced binary outcomes: operate at full capacity or shut down entirely. The machine still worked perfectly. That was the problem. Excellence could not fix exposure. Big Muskie remained operational through the mid-1980s, but its operational philosophy was obsolete. Mine planning had shifted toward adaptability. Contractors wanted equipment they could move between sites as seams depleted and contracts shifted. Environmental regulations imposed reclamation requirements that favored smaller, more precise equipment. Insurance companies raised premiums on single asset operations, citing catastrophic loss potential. Modular fleets won contracts even when their total operating costs exceeded large draglines. The reason was simple: risk distribution. A contractor with 10 smaller machines could lose one to failure and maintain 80% capacity. A contractor dependent on Big Muskie lost everything if the machine went down. Financial models priced that difference brutally. Dealers defected. Parts suppliers shifted inventory toward higher volume models. Service technicians trained on competitor equipment. Bucyrus Aries dealer network, once a competitive advantage, thinned as regional distributors consolidated or closed. The company still built quality draglines, but market momentum had shifted. Operators respected the machines. Contractors bought elsewhere. The brand endured, but market share bled. Respect turned to silence. Environmental regulations, economic stagnation, and changing energy policy converged in the late 1980s. The Clean Air Act amendments imposed stricter emission controls that favored low-sulfur Western coal over Ohio's high-sulfur reserves. Central Ohio coal faced declining demand for its primary product. Strip mining reclamation costs, previously deferred, became immediate liabilities under new state enforcement. The company evaluated options, modernized the operation, shift to underground mining, or close. Big Muskie's operating costs, once justified by volume, became unsustainable as production quotas fell. The machine required continuous electrical supply whether digging or idle. Maintenance schedules did not scale down. In 1991, Central Ohio Coal announced closure. Disassembly took years. The boom was cut into sections by crews who had never seen it operate. The walking mechanism was separated from the house and scrapped. The bucket, still intact, went to a mining museum in southeastern Ohio where it sits today, dwarfing visitors who photograph it without understanding what it moved. The rest became scrap metal, sold by weight to recyclers who melted it without ceremony. The greatest machine left almost nothing behind. Every modern dragline carries Big Muskie's lessons, though few operators know the source. Structural modeling techniques developed for the 4250W's boom became industry standard for analyzing stress distribution in long-reach equipment. Electric drive scaling, refined to handle 13,800-volt continuous loads, enabled the next generation of mining shovels. Operator ergonomics, the insight that crews needed enclosed, climate-controlled cabs with coordinated, multi-function controls, became mandatory across the industry. Bucyrus Erie survived into the 1990s, building smaller draglines and shovels that incorporated everything Big Muskie proved. But the company never regained its innovative edge. Ownership changed hands. The name diluted through mergers. In 2011, Caterpillar acquired what remained, absorbing patents and expertise into a corporate structure Big Muskie's engineers would not recognize. The South Milwaukee factory still builds mining equipment, but the Bucyrus Erie name exists only on old dealer signs rusting in equipment yards across the Midwest. Big Muskie's fingerprints remain in every electric dragline operating today, in boom geometry, in walking mechanisms, in power distribution systems, in operator interfaces. The machine lost. The knowledge won. The final image mirrors the first. Steel, silent, enormous, stripped of name. The future it built survived. The name did not.